Hello, everyone. This is part 2 of the Chapter 6 notes, which will be dealing with energy. And I refer you to page 4 of your note packet. Now, unless you're an advocate for green energy or Don Quixote, you often don't think about windmills in your everyday life, which is a shame because windmills are a very good illustration of the concept of conservation of energy, or where energy comes from and where it goes. So at the most basic level, what this windmill is doing is taking mechanical energy from the wind, converting it into electrical energy, and then that electrical energy is what is allowing me to run this camera and bend your ears. But in a broader sense than that, if you say, well, where does the wind's energy come from? It comes from uneven heating of the planet's surface by the sun. That causes, again, a difference in temperature, which causes wind to rush from one place to another. Where does this heating imbalance come from? Well, it comes from the fact that our planet is heated by the sun. So you have radiation energy, which is providing the wind energy, which is providing the mechanical energy, which is providing the electrical energy. Where does that radiation come from? It comes ultimately from nuclear reactions which are occurring in the sun. So in a sense, if you're running a turbine, you are kind of doing nuclear power by an extremely indirect means. It's a very good illustration, again, of the conservation and uses of energy. So what is energy? One definition is that energy is a scalar quantity associated with the state or condition of one or more objects. So energy does not have a direction. It's directionless. It can be applied in any direction and from any direction. You can also think of it as sort of a capacity to do work. It's a capacity to sort of push things around. A few characteristics is that energy can be transformed from one type to another and transferred from one type to another. But it cannot be created or destroyed. Energy is conserved. So a great example of that, once again, is in our windmill example. All of that energy came from someplace and it went someplace. Also, if you're thinking about, say, throwing a piece of Play-Doh at a wall, I am transferring energy into that Play-Doh, and when the Play-Doh collides with the wall, the energy is used to either deform the Play-Doh and get it to stick. It is transferred into sort of a shock or a bit of a pressure wave in the air, which we experience as sound. And a lot of it is dissipated as heat. The wall gets slightly warmer as a result of throwing this Play-Doh into it. But the critical thing is, every single joule of energy that I put into that Play-Doh when it left my hand has to be accounted for somewhere, either in the deformation, in the sound, or in heat. So that's very important. You have to do kind of accounting when it comes to energy. We're talking a bit here about gravitational potential energy and elastic potential energy. So what do I mean by potential energy? Well, that's energy that is, in a sense, stored and which can be released or liberated later. We'll get into that when we start talking about conservative and non-conservative forces. In gravitational potential energy, that is simply if I have a ball or some kind of a projectile which is above the surface of the Earth, there is some energy that has been sort of stored in that ball. I had to do work to get that ball up there. I had to expend some energy to get that ball up there, and that energy can then be liberated if this is to fall off a ledge and drop down here. The gravitational potential energy is given by the mass of the object times acceleration due to gravity times the y-coordinate. Well, what exactly do I mean by the y-coordinate? Potential energy, or gravitational potential energy, is dependent on what you are measuring the ball relative to. So, for instance, if I have this ball which is perched on a great height, but I have underneath it some kind of table and I say, all right, what's the potential energy of this ball relative to this ledge or relative to the ground, you're going to get two different answers. The potential energy from here to here is greater than the potential energy from here to here. And if this ball does fall here to this table and rests here, it's not entirely devoid of potential energy. What happens if it falls even further? Of course, you're always going to have some kind of gravitational potential energy relative to, the center of the Earth, even if you're on solid ground. So to just sort of clarify things, we have this thing called the y coordinate, which is basically saying, all right, potential energy measured relative to what? Measured to the height above what sort of 0 point. So it's mgy, and we'll talk about this more in Chapter 7. There's also elastic potential energy. If you have a spring and you've pushed against the coils of that spring, and the spring can go sprawling and transfer a bunch of energy to whatever particle you've placed against the spring, that is elastic potential energy. And elastic potential energy is given by 1/2 K. K is something called the spring constant. We'll meet that in the next, well, not in the next section, the section after the next section when we deal with springs. And x squared, which is displacement from some 0 point. For some kind of neutral or uncoiled point, if you will. In this chapter, we're going to be dealing primarily with kinetic energy, and that is energy associated with an object that is presently in motion. So for an object of mass m, whose speed is v and well below the speed of light, so we don't have any relativistic effects, kinetic energy is given by 1/2 mv squared, where m is mass and v is velocity. It's important to note that the SI unit of kinetic energy and every other type of energy is the same as it is for work, or the joule. And kinetic energy is a scalar and does not depend upon the direction of motion. So if something is in motion, it has a particular kinetic energy. You don't really care what direction it's heading. Also, kinetic energy can never be less than 0. If you have no velocity, you have no kinetic energy, but you can't have, again, less than a 0 velocity. And you notice here, you say that the unit of kinetic energy is the same as it is for work. Does this mean that work and energy are the same? Well, the work energy theorem says yes, they are the same. That the work done by the net force on a particle equals the change in the particle's kinetic energy. So total work is given by some final kinetic energy, K2, minus some initial kinetic energy, K1, or it's equal to the change in kinetic energy. You can also say that the total work is equal to some final kinetic energy, K, minus the initial kinetic energy, 0, of just a ball that's sitting and not actually moving. So the total work, the total kinetic energy of an object equals the total work done on that object. Why is this particularly useful? Well, let's say we wanted to determine the total work that was done on the Voyager space probe, the work that was done from the rocket as it left Cape Canaveral, to the work done by gravity, to the work done to speed the probe up by Jupiter and Saturn, and you got all of these different things that you'd have to consider. If we were going to look at this using F equals ma, if we're looking at just forces, you'd say, well, geez, that's a really complicated problem. You've got to consider changes in force as you're approaching the planet. You've got to consider changes that sort of thing. It gets to be a kind of a mind-boggling problem. But given that we know the velocity of the Voyager space probe, and given that we know the mass of the Voyager space probe, we know that the total work of everything that has been done to Voyager over the last 40 years can be accounted for if we just know the velocity and we know the mass, if we know the starting and final states of a particular object or projectile, which is very useful. It makes our life a lot easier. This also holds for both positive and negative work. If the net work done on a particle is positive, then the particle's kinetic energy will increase by the amount of the work. And also, if the work done is negative, then the kinetic energy will decrease by the amount of work done. So let's take an example. We have a 14,700 Newton sled, which is moving along with an initial speed of 2.0 meters per second. A net work is done on the sled of 10 kilojoules. We give this basically a 10 kilojoule push, if you will. If the sled moved to the right 20 meters, the question is, what is the final speed of the sled? What's V2 here, right? So first thing we want to do is that we're actually given the weight of the sled, and we want to find the mass because kinetic energy is dependent on mass. So m in this case is equal to the weight over the acceleration due to gravity. Assuming that this takes place on planet Earth, we can say that that's 14,700 newtons over 9.8 meters per second squared. The mass of the sled is 1,500 kilograms. The initial kinetic energy, sorry about this, is equal to 1/2 mv sub I squared, and the final kinetic energy is equal to 1/2 mv final squared. All right? So we can very easily find what the initial kinetic energy was by simply plugging in 1/2 times 1,500 kilograms, that's the mass, times that initial velocity, which is given to us as 2.0 meters per second. Square that, we solve this, and we find that the initial kinetic energy of this sled was 3,000 joules, or 3 kilojoules. Similarly, with the final velocity, we can say 1/2 times 1,500 kilograms times the final velocity squared is equal to this final kinetic energy. Now all we have to do is solve for the final kinetic energy. What we can say is that the total amount of work in this system is equal to the final kinetic energy minus the initial kinetic energy, which we can rearrange to say that the final kinetic energy is equal to the initial kinetic energy plus the total amount of work. We plug in, we know that the initial kinetic energy is 3,000 joules, because we figured that out already. We're told that the net work is 10 kilojoules, or 10,000 joules, meaning that the final kinetic energy must be 13,000 joules. What we are then able to do is plug and chug, and we say 13,000 joules is equal to 1/2 times the mass times the final velocity squared. Rearranging and solving for the final velocity, we find it to be 4.2 meters per second. Now, you could solve this problem using F equals ma, but it would be, as you can see, or you might imagine, an awful lot more complicated than this very elegant algebraic solution. It took us, 4 equations to arrive at this particular answer. And that is why energy is a powerful and useful tool when solving these kinds of kinematics problems. Right? So let's say that former Orioles catcher Rick Dempsey hits a 155-gram baseball 87 feet or 26.1 meters in the air. And let's say, for the sake of this problem, that he hits the ball straight up. The question that is asked is, how fast was the ball going when it left Dempsey's bat? So this is 26.1, right? So to solve this problem, what we have to note is that after going 26.1 meters into the air, this ball is stationary before it actually returns to Earth. So we can think of this either as trying to determine the negative work done by gravity to get the ball to stop in a distance of 26.1 meters, or alternately, we know that the ball falls from a distance of 26.1 meters to the ground. We also know that the velocity as the ball left the bat is going to be the same as the velocity when the ball has returned to that same height. So to do this, what we say is work is equal to F times S. Force in this case is equal to MA. That lets us solve for this guy, this force here. And the force in this case is 0.155 kilograms, or 155 grams, times 9.8 meters per second squared. Again, we're assuming that this is taking place on Earth, which gives us a force of 1.519 newtons. We can then solve for the work that is done by gravity, either on the ball, the negative work as the ball goes up, or the positive work as the ball comes down. And we find that that work is 1.519 newtons times the distance of 26.1 meters, or 39.6 joules. And we know that the work is equal to the kinetic energy, which is equal to 1/2 mv squared, which is equal to 39.6 joules. So that's either the work done by the bat as the ball is going up to this height, the negative work done by gravity, or the positive work done by gravity to bring the ball back down. You can take your pick, and then they're going to be all the same. We then go ahead, make our substitutions. We substitute once again for the mass. We solve for v, and we find that the velocity was 22.6 meters per second when the ball left the bat. Now, if the opposing catcher caught the ball at the same height at which it left the bat, what was the total work done by the ball on the entire trip? I think you can probably do this by inspection. Because the ball was caught at the same height at which it left the bat, the total work done is 0 because there is no net displacement in this particular case. All right, so let's take a look at another example. We have a loaded grocery cart with a mass of 33.3 kilograms rolling across a parking lot in a strong wind. You apply a constant force, and the force vector is given as 30 newtons times I cap minus 40 newtons times J cap, as the cart is undergoing a displacement of negative 9.0 meters times I cap minus 3.0 meters times J cap. So first question is, how much work does the force you do, how much work does the force you apply do on the grocery cart? So how much work are you doing on the grocery cart? And then it's also asking us to find to what extent this shopping cart was decelerated, or what its initial velocity was, right? So in this case, whenever you have vectors that are nicely laid out in this particular form, the dot product is relatively easy to find. So you see W equals force vector dotted with the displacement vector. So you say 30 times negative 9 plus negative 40 times negative 3. You add those together, and you see it is negative 270 joules plus 120 joules equals negative 150 joules. This makes sense. You would be doing negative work in this case because you are opposing the direction of the displacement and you are slowing the cart down. All right. And what you can kind of, so that's, again, completely reasonable to say that this is a negative amount of work that is being done. The total work, we're looking at part B, is equal to the final kinetic energy minus the initial kinetic energy. And I'm going to do something a little bit eccentric here. I'm going to assume that the final kinetic energy is 0. Why am I doing that? Because we're only concerned with this particular displacement. We're assuming that outside of this, the cart either has come to a stop or we really don't care what happens to it. We're only looking at this particular displacement. All right, and as we're only looking at this particular displacement, we can pretty much assume that the cart has stopped. So we say that the final kinetic energy is 0, and the total work is equal to the negative of the initial kinetic energy. So we say negative 150 joules is equal to the negative of the initial kinetic energy equals negative 1/2 mv sub I squared. So all we have to do in this case is solve for V initial. If you multiply both sides by -2, you find that 300 joules equals mass times velocity squared. We know that the mass is 33.3 kilograms, and we can solve for the velocity as being 3.24 meters per second, meaning that you slowed this cart down by 3.24 meters per second as you're going across this particular displacement. So that's pretty cool. Let's take a look at one final problem here. A child applies a force parallel to the x-axis of a 10-kilogram sled moving along the frozen surface of a small pond. The child is controlling the speed of the sled, and we have force given as a function of distance. So as we remember from the previous lecture, what is the work in a case like this? The work is simply the area under this curve, right? Now, we don't have any sort of convenient calculus function that we can use here and take an integral. I know you were all very excited to take an integral. I was very excited to take an integral. But we do have the next best thing that we can do, which is to determine the area of this triangle. Okay. So from 0 to 8 meters, we can find the area of a triangle, right? That's 0 to 8. This is the base times the height, and 1/2 base times height will give us the area. So 1/2, 8 times 10 is 40 joules. Similarly, from 8 to 12 meters, the base is 4, the height is 10, 1/2, 4 times 10 is 20. And to find the area of the whole shebang, the base is from 0 to 12. The height is still 10, so it's 1/2 12 meters times 10 newtons, or 60 joules. Incidentally, you may have noticed, if you've ever seen a food item which is packaged for a foreign market, or packaged for a market which is both the United States and elsewhere, like somewhere in Europe or somewhere in Britain, for instance, you'll sometimes notice that the energy content is given in both kilocalories and in kilojoules. So if you're doing your physics homework while you're eating your bowl of muesli imported from Germany, you might be saying to yourself, hey, wait a minute, a calorie is a unit specifically of heat energy. We're used to, kilocalories with a big C, and the kilocalorie is defined as the energy needed to raise 1 liter of water 1 degree centigrade at sea level. So you see this, you say, okay, you got energy measured in kilocalories and energy measured in kilojoules. Does that mean that heat and work are related? The answer is yes, they are actually the same thing. Heat and work are the same thing as stated in the first law of thermodynamics, which is a topic for another course. If you take any chemistry courses or further physics courses, you are going to see that heat, work, energy, they're all different ways of saying the same thing. And fortunately for us, that's the case, that we're able to convert heat energy into mechanical energy. That's how a steam engine works. In around 1750, a man named James Watt and others in England were doing experiments with steam engines to see how you could convert steam energy into useful mechanical energy. And the name Watt is something that we're going to be seeing an awful lot in our next lecture when we talk about power. So be sure to tune in next time, and we will be talking about power.